I thought we could try to make it our way through the two notebooks and the two videos that correspond. There's one where, let's see, it's this one, 3B More Details, where Rachel sort of reviews stuff that she's talked about in the previous videos. And I kind of, she talks about randomized SVD. We didn't pay much attention to that, so I don't think I'll do too much with it here. But yeah, I think it's an interesting topic, but it's, for us, all we care about for this class is being able to use SVD, and we've already done that, using it to factor a matrix. So I'm going to skip over that section. Okay. I wanted to go over this, this example that Rachel has picked out from this book called The Drunkard's Walk by Leonard Mlodinow. He's an interesting guy. He was a student of Feynman for a while. He was a postdoc at Caltech. He was a student of Feynman, and then I'm not sure what happened. He's not a physicist, or he's not working as a physicist anymore, but he's a writer now. So, but anyway, he wrote this interesting book, The Drunkard's Walk, and there's a neat example in here, which Rachel has picked out to help us understand Bayes' theorem. And so Mlodinow went and was tested for HIV, I think in 1989, I think. And his doctor told him that that the test was positive, and that therefore he had he has a 1 in 1,000. Sorry, he has a very high chance of having HIV. So he thought about it and realized that was not true. And so this is where we're going to sort of understand why that's not true. So what happens with the HIV test is that it produces a positive result. We know that it has a false positive probability of 1 in 1,000. That is, 1 in 1,000 people who don't have HIV will show up as having HIV. And so the doctor said, well, that means that there's a 999 in 1,000 chance that you do have HIV. And so Mlodinow thought about that and realized it wasn't true, and this is his reasoning. Okay, so in a very brief sentence, this is how Mlodinow solves the problem. He says, let's prune the sample space to include only those who tested positive. So that means if you have, let's say we have 10,000 people. 10,000, okay, here, there's a previous paragraph that sets this up. So imagine a sample space that has 10,000 sort of people in the general population, which are generally heterosexual and non-intravenous drug using. And also, I think they limit the population to males because this was the sample at that time. Mostly males were being tested for HIV, white males. And so in this sample, according to the CDC, which is the Center for Disease Control, about 1 out of 10,000 people will test positive because they have HIV. And the false positive rate is 1 in 1,000. So that means that if you have 10,000 people who are tested, you're going to end up with 11 positive results. 1 for the person who has HIV, and 10 for the people who are false alarms that don't have HIV, but were given a positive, that the test turned out positive. So that means that 1 in 11 of the people who tested positive are really infected. And so his doctor told him that the probability that the test was wrong was 1 in 1,000. The probability that he was healthy was 1 in 1,000. But according to this way of looking at it, which is the right way of looking at it, only 1 in 11 people who test positives are really infected. So his chance of having, the chances are 1 in 11 that you have AIDS, that he has, not AIDS, but HIV positive, that he has HIV, that he's HIV infected. So the chances are 10 in 11 that he's not HIV infected, if this makes any sense. So the way that he solves the problem is he looks at the sample space. He looks at, and he limits the space. He prunes the space down to only the people who tested positive. for HIV, and then he realizes that only one of these people really has HIV. 1 in 11 of the people who tested positive really has it. So this is a simple way to break down the problem and get an answer. And notice that it's 2 paragraphs, right? Well, and this summarizes it. Okay, so 10,000 people, total people, 11 of them test positive. Of the people who test positive, 10 of them are actually not infected with HIV, and 1 of them is. So that's sort of the table that summarizes the result. And then here's the punchline is that there's only a 9% chance that the test was correct, and that Mlodinow was actually, there was only a 1 in 11 chance that the test was correct. And so Mlodinow was actually HIV negative, it turns out. So, I'm sorry, that's not the way to interpret this sentence. There was only a 1 in 11 chance that the test was correct. And I don't know if you can actually, I mean, he's still alive and he doesn't have any signs of the disease, so he's actually HIV negative. So, yeah, so that 10 in 11 chance that he wasn't infected with HIV, that was as a result of the test, and now we know that's actually the case because he doesn't have it. Okay, so you might say, well, okay, that's it. Why, it's 2 paragraphs. We have to struggle a little to understand it, but it's pretty transparent after you think about it that that's the right way to think about the problem. So now I'm going to go and show you another way to do this problem using Bayes' theorem, and it's going to take a couple of pages, and you're going to wonder, why am I doing all this work and look at all those nasty equations and everything to get to the same result? And the answer is that Bayes' theorem and the Bayesian method is so important that you're going to encounter it again and again and again, and it helps you to solve problems that are much more complicated than the simple one that we just solved using a different method. And so it's worth it to learn Bayes' theorem and more importantly, how to use Bayes' theorem, because Bayes' theorem is how people infer the truth from evidence. And this is going to become more and more important in machine learning. Causality is a really big topic, to establish causes for something. And that always involves using Bayes' theorem. And this year, I think 2020 is the year in which, I think 2019 it really started, but 2020 there's a lot of emphasis going to be on identifying causes in machine learning models, or using machine learning models to identify causes. Okay, so we can start with this. So here's a review of the facts. But wait, first I wanted to show you Bayes' theorem again. We saw this last time, but it's worth seeing it again so that you'll just sort of, the more times you see it, the more likely it is that it will be branded in your mind, and that's what I'm trying to get at. First of all, everyone can see my screen, right? I'm not just talking, right?
No, you're good.
Okay, thank you. Okay, so consider 2 events, A and B. The probability that A and B occur together can be written in 2 ways. One way, and this is the mathematical way of saying probability of A and B occurring together. It's P of A comma B. That means A and B are both occurring together. And that can be broken down as the product of the conditional probability, the probability that A occurs given that B occurs. That's what this bar means, given that. So the probability of A bar B means the probability that A occurs given that we already know that B has occurred. And then multiply that by the probability that B has occurred. And you can sort of see in a reason that it is logically true. That, in other words, if I know that if I know the probability of A given that B occurs, then if I multiply that by the probability that B occurs, that should give me the probability that A and B occur. And you can also write it the same way in sort of in a reverse manner. You can switch A and B, and you can write the product of the probability that B occurs given that A occurs times the probability that A occurs. And that'll give you the same result, the probability that A and B occurs. So this thing here is called a conditional probability. If you haven't seen it before, you will see it again if you ever try to read machine learning papers, this idea of conditional probability. So I've sort of broken that down. P of A is the probability that A occurs, P of B is the probability that B occurs, and these are the conditional probabilities. Define them. This is what I already said in words. And so Bayes' theorem is just the statement that this thing here, the right-hand side of these two equations are equal. That is, this equals this. Okay, and then stated, simply that's what this means right here. So you look at that and you say, well, what good is that? Why is that so important? Well, I want to do something that I should have done before. Suppose we have a hypothesis about the world. We could call it H. And then we have some data, and we can call it D. So then we can let's let H and D take the place of A and B, and then we'll see a more interesting application of Bayes' theorem. So I'm going to say the probability of H given D times the probability of D is the probability of D given H. Yes. Did somebody have a question?
No, I was just talking to myself as you were writing.
Okay, okay, that's fine. Okay, so here's what it looks like. So this is how you can think about hypothesis, that something you're trying to find evidence for or support for, and data. And a hypothesis could be some kind of a model where you have some parameters, like if you're looking at movie reviews, the hypothesis could be that the review is a positive review or a negative review. It's something you're trying to find out about the world. So generally, the useful form of Bayes' theorem is when you divide both sides by this P of D. Let's see, there we go. That. Yeah, but there's a better way to write that. Sorry. I'm doing tech here, LaTeX. P of D, P of H, and P of D. Now it's going to come out looking like a fraction, which is what I want. So there it is. So that's the statement of Bayes' theorem in the way that you use it in hypothesis, in machine learning and hypothesis testing and so on. And generally, the probability of H given D is the probability that your hypothesis is true given the data that you have in hand. That's always what we want to find out, okay? We have some data and we want to figure out whether a hypothesis is that we've thought about, that we've created, a model or something. We want to figure out if that's true. Okay, so it can be written as the product of P of D given H. That is the probability that we would have gotten this data if this hypothesis were true, times the probability that the hypothesis itself is true, divided by the probability that the probability of getting the data that we got. So these are the things that that we work with, and they're called. I should write this. This thing here is called the posterior. You'll hear these terms used. Every one of these terms has a name, by the way, so that's what I'm trying to.
I have a question.
Yes.
What exactly does it mean to have the probability of the data?
That we will find out. In other words, we've seen it. The probability that we've seen. The probability of seeing this kind of data, like suppose if you've, let's see.
And like, how about weather, for example?
Yeah, like say if you have a rainy day, then you can look in the whole history of meteorological records for your area and figure out what the probability is that you would see a rainy day. That's what that would be.
Okay.
Okay.
Thank you.
You're welcome. Okay. Let's see. Now this thing here is often referred to as the likelihood. Likelihood of the data. And that can also be computed, as we'll see in this example. P of D is the prior. Let's see. Sorry, I should have typed this up beforehand instead of making you wait while I type. But I'm almost there.
It's okay.
Just FYI, I think you overwrote something in the main equation. The prior was P of D, and it got overwritten as...
yes, I see that. Yeah, thank you. So that was the likelihood, and this should be P of D, yes.
Mm-hmm.
Thank you. Thank you for spotting that. Okay, and then so we've got the prior, and we've got the denominator, which is the... I just did that again. Let's see. This is the prior, and then... Sorry, we'll get there in a second. And then finally, the denominator part is the evidence. So these are the pieces. Okay, let's see what it looks like. I need to just put line breaks there. Okay. So these are the names for the terms. Yeah. Okay, and so we're going to talk about all these terms in the context of this problem that we're looking at now. So so this is the thing, the model or the structure to keep in mind. This is what we're going to be applying to our problem here with the HIV test result. So let's review what we know. This guy was diagnosed as HIV positive in 1989, at which time the false positive rate of the HIV test was 1 in 1,000. And I've checked them, by the way, it's still 1 in 1,000. According to the CDC, Center for Disease Control, the incidence of HIV infection in the ordinary population is 1 in 10,000. I think the ordinary population of white males, I think, I think I put some reference to that at the bottom. Let's see. Probability of, well, we'll get to that footnote later. Anyway, so here we are. This is the three things that we know. We want to determine the chance that he was actually infected with HIV. The probability that any person who received a positive HIV test result was actually infected with HIV. So we'll proceed by translating our problem into the language of probabilities and conditional probabilities. So the probability that a person in the sample is or is not infected with HIV, this is the priors, is the probability of HIV is 1 in 10,000, which is 0.0001, and the probability of not having HIV is 0.9999. Those are the priors, the things that we already know about our population. The false positive rate is the conditional probability that a person who doesn't have HIV would test positive. And this is what we've called the likelihood. So the probability of a positive test result, given that you're not HIV infected, is you could still get a positive test result 1 in 1,000 times. So that's the false positive rate. What we want to determine is the probability that a person who's given a positive test result was misdiagnosed as HIV infected. So that would be the probability that a person doesn't have HIV that the person isn't HIV infected given that the result was positive. And here the bar means not. Okay, I think you're familiar with that. And this is what we call the posterior. And the posterior is always the prior probability updated with knowledge that you have. So it's an updated version of the prior. So surveying what we've done so far, you can see that these pieces are right for the application of Bayes' theorem, right? These are two conditional probabilities where the two variables are reversed, and that's a sign that you can apply Bayes' theorem, right? And so we can write down Bayes' theorem for this situation. Just straight application of the structure that I gave you before. And then we solve for the posterior, which is what we want to find out. And then this is what Bayes' theorem says about this problem. And so our job is to compute all three of these pieces, to make sure that we can compute all three of these pieces. And when we do, we can put them together and figure out the answer to our problem. So we already know two of the three pieces on the right-hand side of the equation, namely the likelihood, the probability of a positive result given that the person isn't HIV infected, that's 0.001, and the prior, the probability that the person is not HIV infected, that is, we know that the probability that the person is infected is 1 in 10,000, so the probability that the person is not infected is 0.9999. So 1 minus 1 over 10,000. So now all we have to do is compute the third piece, which is this thing, probability of getting the probability of getting a positive result. That is the probability of the data, and it's the name we gave for it is the evidence. So we reason that if a person tests positive, there are two possibilities. Either the person was infected with HIV or they weren't. And so we can calculate this thing as the product of two terms, the probability that the person was positive because they had HIV, the probability that the person was positive and they didn't have HIV. And that's these two terms. And here we've hit a snag. We have, if you review what we know know this guy here, we know this guy here, and we know this guy here. The only piece of this that we don't know is this. This is a really important number, by the way. It's a number that quantifies the test's effectiveness in detecting HIV. And you can imagine that the drug this is the number that the drug companies have to make as close to 1 as positive. Okay, and they can't make it exactly equal to 1. But if it's less than 1, that means that the test sometimes misses detecting the disease, and that's bad, right? So that's called a false negative, a missed detection. But as I said, it stands to reason that the drug companies have worked hard to make this number close to 1. So let's forge ahead with that assumption and see where it goes. We substitute values in this equation, substitute everything we know in, and now we don't know this, but we'll say, okay, we think it's very close to 1, so let's just put 1 for it. We do that, and we end up with this equation. And notice that that because of the way these numbers are, it doesn't much matter that this number, we don't know this number exactly, because it gets multiplied by 0.0001. So whether it's 1 or 0.99 or 0.98, it's the other term dominates. So this is the result. So it turns out that our approximation was justified because let's see. I won't edit the text, right? There's a mistake there I just saw. But it turns out that our approximation was justified because, like I said, the second term dominates. And actually, I went to the internet and looked up what the specificity of the AIDS is, that the HIV test is. That is the probability that it gets a detection if the person really has AIDS, and really has HIV positive, and that number is like 99%. It's like 0.99. So the actual known value is 0.99. We said it was 1. It doesn't much matter because the second term in this equation is much bigger. So now and I wanted to mention that if you look carefully at the table in section 2, the table where we did it the easy way, they actually made the same assumption implicitly, but they didn't talk about it. In other words, the person who had the one person in the sample that had HIV actually tested positive, right? It won't always happen that way. It only happens 99% of the time that a person who's really HIV positive will get a positive test result. So, yeah, so now we have, yes, sir.
A quick question. What is the difference between the left-hand side, the probability that it is positive, and the conditional probability of testing positive given HIV?
Okay, that's a really good question.
Because
so
that's that second part, testing positive given HIV, we've assumed to be close to 1.
Yes.
How is that different from the probability that it's positive? Yeah.
Okay, that's a really great question. Okay, so this is the probability that the test is positive in the population of people that already have HIV, that do have HIV. In other words, a probability that an HIV-infected person, given the test, will come up positive. That's what this is.
Right.
Does that make sense?
That
is the probability
that's based on the sample. So that's testing positive based on the sample of HIV.
That's right. The sample of people who have HIV infected, people who are HIV infected, which is a small subset of the whole population, right? This probability is the probability that a test will come up positive if anybody took it.
Of the entire population, not a sample.
Of the entire population. And we did specify that the population of males, white males who aren't drug users. I think that was the special case. That was the case. That was our sample. We thought, as we said in the beginning. Okay.
Yep.
So there's a big. These terms look. I like that you asked that question because these terms look the same, but they're very, very different, right? This number is going to be very large, very close to 1. Because the drug companies worked hard to make this HIV test, right? This number is going to be close to 1. This number is going to be much less than 1. The probability that a person in the general population is going to get a positive result is going to be way less than 1. Okay, so that's a really good question. I'm glad you asked it.
Yeah, it's a difference between sample and population.
Yes,
the weight.
That's right. So, so that's it. That's the so we've gotten. The last line. Okay, now we have all the numbers. Now we put all the numbers back together and we compute the posterior, the probability that a person who didn't have HIV, the probability that a person who received a positive test result really didn't have HIV. And that probability turns out to be, putting just those numbers together, the numbers that we just, all the 3 pieces that we just figured out, right, turns out to be about 0.9 or 0.91. Okay, so the probability that Milano was infected with HIV is 1 minus that probability, 1 minus that. And it's 0.0909, so it's like 1 in 11. It is 1 in 11, 9%. Okay, so we got the same result, but here we got it by a much more principled way of thinking that, well, not more principled, but more general, more generally applicable way of thinking. So you might think, why did I go to all this trouble to get a simple result that we could get by 1 paragraph of thinking, this result here? And the answer is that this method is nice applied to a simple problem, but it's not so nice if you have a more complicated problem, whereas the Bayes method will be applicable to much more complicated problems. And if you ever want to read machine learning papers, you'll see this gets used all the time, and it increasingly more as the years go by. People are using Bayesian reasoning. So now that's your introduction to Bayesian reasoning, and you should now be able to follow discussions that refer to Bayes' theorem and Bayesian reasoning. And that's what I wanted to do with the first part of this lesson. So this is something that Rachel put together. It was in the original notebook. It's a quick review of the naive Bayes classifier. And now that you've seen our discussion of Bayes' theorem, this will be very easy for you to follow. And I've already done this in the last notebook anyway. So Rachel has a discussion about numerical stability, which is interesting, but I think you guys can go through it on your own. It's really interesting to understand how computers use numbers and how computers are limited in their calculations, the real limitations that you have in terms of memory and time and so on. So there's a really interesting set of numbers that she points to that everybody should know, and it's good to get familiar with these numbers. So I'll just let you guys do that. Rachel put together naive Bayes in an Excel spreadsheet, which might be interesting for you to look at. But I think, given that I did this whole thing in the last notebook, this thing here, I gave a pretty detailed discussion of the naive Bayes classifier. So if you've missed that last class, you can go back to this notebook, the notebook number 3, where this was a really long notebook. But I did give a pretty complete discussion of the naive Bayes classifier applied to the IMDb movie reviews. And there, the hypothesis that we're talking about, the model of the world, was that we're trying to test was the question of whether a review composed of a given set of words is positive or negative, is likely to be positive or negative. So that's that. So then the main part of today, I think I wanted to spend talking about the regex. I don't know how, I think they call it regex, or maybe regex, regular expressions.
I've heard both.
Regex.
I mean, yeah, it's just that, but the word, since it's regular expression, it's not regular expressions.
Yeah.
I would think I would prefer to call it regex, but I've heard it called regex, as you said. So regex is really a mini language that is used to parse strings. And if you've seen this, you know you're going to be familiar with everything. And say if you haven't, then this will be your chance to get a solid introduction to it. I must say that I just learned this myself, just going through Rachel's notebook and some of the references that she gave. I've seen regex many times over the years, but I've never bothered to delve into it because it just looked like a bunch of gibberish to me. but I want to show you that it's not, and it's really a language, and the first thing you do when you start to learn a language is you start to learn some of the vocabulary, and then you learn how to put together the vocabulary. So that's what we're going to do. Regex has a whole bunch of things called metacharacters, and there's always a distinction between metacharacter and literal. So let's get that out of the way first. A literal is basically literally a text string, a character in a string that you're trying to find or search for, like a period or an exclamation point or a digit 2 or a parentheses, left parentheses or a right parentheses. These are the actual characters in the text string that you're searching for. That's what a literal is. Okay, so now that we've gotten that out of the way, what's not a literal is a metacharacter. A metacharacter is a special character that has a special, that is a part of the vocabulary of this mini language of regex. And the backslash is a special metacharacter that says make the following metacharacter into a literal. So in other words, the simple application is if you want, so since let's just scroll down the list here. This is a metacharacter that means match one instance of any character. It's a wildcard match, so it's a period. But what if you actually want to try to match a period? Then you get confused because the period is an actual metacharacter in this language. So to get rid of that, or to overcome this problem, we put a backslash in front of that period, and that makes it into a literal period, right? So there. So this thing means, if I want to match a period that is the last character in a string, it turns out that this $ is the metacharacter for matching the last character in a string. If I want to match a string that ends with a period, then this is the regex expression to do that, right? the backslash, the escape in front of the period means treat that period as a regular literal period rather than as a meta character, as a vocabulary word in regex. Does that make sense?
Yes.
Slash period. Okay, there's a bunch of other characters that have meta characters in regular expressions. This is a group of them that is interesting. The ones with special characters with backslashes in front of them. /D means match one instance of a digit. That's the D for digit. /D means match one instance of a non-digit. And /W means match one instance of an alphanumeric, and that is A through Z and 0 through 9. That's an alphanumeric. And /W means /W means match one instance of a non-alphanumeric, which means that the character has to be a symbol. I think what I thought at first was non-alphanumeric should include spaces, like void space. I'm not sure if that's the case. I think that it has to be it doesn't include white space, but we can check that. So I think it means non-alphanumeric, which means it's like a symbol, like a plus sign or a question mark or an exclamation point or a pound sign, one of those symbols that we have. Then the S means match one instance of a white space, and /S means /S means match one instance of a non-white space character. So these are important selectors for what you want to match. And then, as I said, dot is a wildcard match. It means match one instance of any character. Question mark means match 0 or 1 instance of the preceding character. So this is like an optional match. So if I put question mark 1, that means I want a string that I'm asking whether the string has any ones in it, but it can return a positive result even if the string has no instances of 1 in it. So it's an optional match. Plus means match 1 or more instance of the preceding character. So that makes it a mandatory match. A star means match 0 or more instances of the preceding character. So, for example, if I put 2 star, that means that means I'm asking for a string that contains 0 or more 0 or more 2's in it. But if I put a plus in front, if I put 2 plus, then I'm asking that the string contains 1 or more 2's in it. I want to match I want to match 1 or more 2's. And then these are quantifiers. The curly brackets mean match a string that contains 3 instances of the preceding, exactly 3 instances of the preceding character. So if I put B and then these brackets, then I want to match a string that has 3 B's in it. And then the other way you can use this is M, which means match a string that has at least, sorry, I had this backwards, at least M times, where M is less than N, right? And it has to occur at least M times and at most N times. I've got this backwards. At least M times and at most N times. Right. So, so you know, so so there are the square brackets. Means that whatever is in the square brackets match exactly 1 instance of it. So if I have square brackets A through Z, that means match exactly 1 alpha character, that is A through Z. The caret is kind of special because it has 2 interpretations. One, when it's occurring inside of these square brackets, it means logical not. So square brackets caret A through Z means match exactly 1 instance of a character that is not an alphabetical character. The other use of caret refers to it refers to the character at the beginning of a string. So caret capital A means match A if it is the first character in a string. and then it has a matching thing, a matching end character that is the $sign. So X dollars refers to the character X at the end of a string. If it's B dollars, that means match the character B if it occurs at the end of a string. If you want to match a period at the end of a string, then you have to use the escape, the slash character to, because period is a meta character, and we're interpreting it as a literal here. We want to match a literal period at the end of a string, so we have to do this. Okay?
Sorry to interrupt.
Yes.
Quick question. Right there, X dollar symbol. I thought that was X asterisk for some reason in Regex. It's been a while for me.
Yeah, the asterisk back here means match 0 or more instances of the preceding character. Okay, so it's kind of a wildcard, but it's optional. It could have 0. You might be, it might be some other language that that Star has. Star has this interpretation of wildcard in some use cases, but in this language, so that, in other words, the asterisk could mean anything. It's a wildcard in some languages, but in Regex language, it's an optional match. Okay.
Got it. Yep. Yeah. Thank you.
Yeah. So these are just the pieces of the language, and you can't memorize them if you just look at them once, unless you have a super memory. But as you see them, as you get familiar, these are basically, this is almost 100%. This is like, there's other things in Regex language, but this is like the most of it that you'll ever need, right? And then the last thing I wanted to show you was the group. Well, let's see, a couple of examples. I think we got to this. Z matches Z if it's the last character in a string. /W, remember what /W means? It means an alphanumeric. So it means match, sorry, I made a mistake here. W is an alphanumeric. That's what we said here. And in here, I said it was a digit, so that's wrong. So, so W is match an alphanumeric character. In other words, if a string ends with any alphanumeric character, then match it. Yeah. And then the round brackets have another meaning. They mean match a group of characters in the order they're given. So remember, with this, with the square brackets, it refers to one character, and it can be any one of these characters that you specify inside the square brackets. But the round brackets have a different meaning. They mean match a group of characters in that order. So parentheses dog, close parentheses, means match a string that contains the characters DOG in that order. And then this is a summary that I got from this reference. This is a really good reference, by the way. We might want to visit it. Let's visit it. Regex 1. It's this brief tutorial in, let's see, I want to go to this first lesson. It's a very brief tutorial, and you can do this in probably 1 or 2, probably 2 hours is enough to get through all the lessons. And it just gives you all these little examples, and it takes you through all of the different vocabulary words, for example. So here it gives you a problem. You want to match, you want a regex expression that will match all of these things.
Just
so there's a lot of ways to do this. One way is we can match any string that has an A at the beginning of it. Let's see. Wait a minute. A at the beginning. I'm sorry. That's the beginning was caret.
Caret,
right. So match any string that has an A at the beginning, or see that begins. Maybe I have to put the caret on the other side. Caret A. Yeah, and that matches all of these things. There's lots of ways to do this. You can say these are all alphanumeric characters, so I can say W. That will match the first A, but now I can say, let's see, I want to do this let's see, any number of times. So I can do this, I can do something like this. I think this will work.
Curly bracket.
I don't add a plus sign.
Yeah, I could. No, that doesn't do that. Let's see. let's see. Suggestions, if you want to.
I just
The
did
curly brackets.
in the
As
bracket.
in like
Yeah, you
just,
could go any
forward
number.
slash
Right.
W plus.
Right. So what I had was /W, /W, and then plus, right? Because
Curly
that gives you.
Uh-huh.
Let's see. I need a plus sign. Yeah. So that says match one or more instances of this thing, right? And
Mhm.
this thing it says any alphanumeric, so that could work. The other thing that can work is well, dot only matches one instance.
We could prep
So,
something.
but I could go dot plus, and that'll match all one or more, right?
Yeah.
But notice that dot star. So remember, dot is any character. Dot star, dot asterisk. It says 0 or more, so that will also work.
Why would star and plus both work?
Because but one of them says 1 or more, and the other one says 0 or more. And these things both, remember, it's the or more that it's matching.
Or
1
more,
or more,
yeah,
right?
yeah.
Or 0 or more, right? So that's lesson 1. Okay, so now we've already done lesson 1. Well, let's do one more. Let's see. How do you go to the next lesson? Oh, I did that. I have to do. I have to pass the test in order to move on. So W plus, that was our solution. So we move on to the next lesson. And now, let's see. It wants us to write a pattern that matches all the digits in the string below. Okay, we want to match all the digits in the string. So it has to be, again, any character plus, and that'll work. It's the same solution. But there's other ways to do it, I'm sure. But let's see.
The backslash D.
Matches. Yeah, D. If you try /D, it will pick out the digits, right? It will pick out one digit, right? If you type /D plus, it will match all of the. It will match all the instances of digits, but it doesn't match anything that's not a digit, right?
Yeah.
If you do this, if you do capital D, it matches everything else. I guess it does include spaces. Anything that's not a digit, including a blank space, I think gets matched. It matches, but it's one. Let's see. But it's consecutive instances, right? So you have this ABC, and then it stops, and it doesn't match the XYZ because that's not in the consecutive. This means a consecutive series of characters. Again, here it's going to match up to this apostrophe or whatever you call it, a quote mark, but then it stops, and it doesn't catch the last quote mark because that's not in a consecutive series. Okay, same thing here. Okay, so anyway, I highly recommend doing these lessons. It doesn't take much time, and you'll really have a good understanding of a good basic understanding of regex when you're done. But back to our lesson. What Rachel started with is a common problem. Say match phone numbers. Match phone numbers. Given a text string, tell me whether it's a phone number or not. And she gave several tries to do that. You have to make this work, by the way, you have to, I don't think you need this. But I did have to do this. You have to import this string package, otherwise it doesn't work. You find it doesn't work. So define a bunch of phone numbers, and she already knows the answer. This is not a phone number. It's an address in San Francisco, but it's not a phone number. So string.digits is just a way of matching to digits. So she first starts with a function that returns true if the characters are digits or dashes or spaces or parentheses, because those are the common characters that you'll find in a phone number. But you can already see that there's a problem here because phone numbers have to have a special ordering. You can't just put a jumble of characters that are digits and plus signs and digits and minus signs and parentheses and spaces. That won't work, and we see that. So she does this assert check, which remember, assert returns nothing if the statement is true. Otherwise, it will raise an assertion error. So she's checking whether these things are phone numbers, and check that it's okay. Assert that it's not a phone number. So all this works. Okay, but then try this one. Another possibility, just these 4 digits. See if that's a phone number. And if you do the assert, you'll find that you'll get an assertion error because it doesn't. Okay, it won't catch that that's not a phone number because the simple function that she created here, which she knows isn't going to work. She's just giving you this as an illustration. This little phone number checker doesn't work because it's not paying attention to the ordering. Not only that, it has to have exactly, a phone number has to have exactly 10 digits in it, right?
Yeah.
And so you know this should fail. So, but it doesn't. Assert, wait a minute. Oh, because I think I think you ran those. I ran the other one. Yeah, I ran the other definition earlier. So this one still doesn't work. Put that in there, and we get an assertion error because the function that we defined doesn't check that there are exactly 10 digits. So now she figures, okay, let's make the test nicer. We'll make sure that we have exactly 10 digits and try that. So now what happens? It all works. But then what about, this string? What about a string that has 10 digits in it, but they're organized they're organized this way? Is that going to be a phone number? Let's see. It says that it's, let's see. I just wrote that so I wouldn't see the assertion errors, but you can do it this way. And it throws an assertion error. It says that it's not a phone number. It has exactly 10 digits in it, and so it should be a phone number. So anyway, this is so Rachel's just doing these examples to show you that we need something better than that, and that's and that's why we need regex. Okay, so regex can do that. So one way to do it is, the square brackets. Remember, square brackets 0-9 means match exactly one instance of a digit between 0 and 9. Every square bracket matches exactly 1, and then the dash matches exactly 1 dash. There's the 3-digit second group of 3 digits, and there's the third group, which should have 4 digits, and that'll match a U.S. phone number. But then, that's kind of, you don't have to do it that way. You can be smarter about it. You can do it this way with /Ds, and then you can do it even smarter by using the exact quantifier, that is, match exactly 3 instances of digit, and then match a dash, and then match exactly 3 digits, and then a dash, and then exactly 4 digits, and that will match a phone number in that format. And of course, you can go one step further, and you can say, well, I want to match phone numbers that use the the parentheses to indicate to set off the area code. You can figure out how to make a regular expression that will do that as well. You ultimately probably want to be able to match a phone number in a valid form. So it could be, some people specify phone numbers by using periods as the separators instead of dashes, and some people use the parentheses around the area code. Some people just use spaces between. So you want to be able to. Some people might not even use any blank space. They just might give the string of 10 digits. So if you wanted to write a real phone number classifier, you'd have to take into account all those special cases, which might be fun to do. Review of these unexact quantifiers. Remember, the question mark is 0 or 1 instance. The star is 0 or more instances, and the plus is 1 or more instances. So now what Rachel really wants to do, and so this is the stuff we just went through, the little thing that I put in for the vocabulary of the dictionary of the regex metacharacters, and now we're getting a little more familiar with them. So now what Rachel wants to do is revisit tokenizers. Let's see if we can build our own tokenizer. And I have to admit that I have not gone through this section yet. So let's just go through it together and see if we can understand it. So so we're going to import this regex. The regex package is called RE. So we first have to import RE. Now, RE works by, you have to make a valid expression by, and a valid regex expression and enclose it between these quote marks. And then it will sort of compile what your regex expression. So this, in what I've emphasized, or what I've underlined here or selected here, is the regex expression. The quote marks tell the regex package that we're giving it a regex expression. And regex compile means, compile this thing so that we know what we're looking for. And so let's see. So this says regex punctuation means find one of any of these characters. I think that's all it is. Let's see.
I thought the curvy brackets like that, the parentheses, were to match an ordered string. So aren't we telling it to match string in that order?
Yes, you're right. So we're telling it to match a string that has an ordered string that has a bracket, a square bracket, an escape in front of a quote mark means a literal quote mark. An escape in front of an apostrophe means a literal apostrophe. Well, no. See. So quote mark must, and then what? Why do we have to do that? And then this and this and period. So I'm not exactly sure what this thing does. Apostrophe, regex apostrophe, I think that's what this one means. Regex compile this. I'm not sure what it means when you add the R in front. I think the R means, let's see. I am not sure what. So sometimes you add the R in front of this, in front of these quote marks, and sometimes you don't. And so I'm not quite sure. It looks like when you don't add it, you mean a literal string. And when you do add the R, it means a literal string, because that's what we're doing here. We're matching a special sequence of characters. So here we're matching an N apostrophe T. Here we're matching an apostrophe S. So these are common occurrences in the English language that we're trying to look for. The way words can end. Multiple spaces. So we have a space with a star, meaning multiple spaces with a star means replace multiple spaces with just one space. So
if I can go about the first one, basically the how's it called, the parenthesis is so that we can return the result. So you can see that in the simple tokens part, it returns what it finds. So parentheses shows like what to find. So the whole thing.
Yes.
But
so the
square bracket then says that the order is unimportant. It just says that find all punctuation in that space. So it's just kind of an or any of these.
That's right.
And,
that's right.
And the slash will just mean that this find literally like the like what you said before.
Yes.
So so all these things.
So so this is great. Thank you for that. Shidrius? Okay.
Gedris, yeah.
Gedris. Okay, thank you. Thank you for that. So I'm wondering why we didn't put a slash in front of the period and another slash in front of these parentheses, because they're meta characters.
This one I don't know.
Yeah. Anyway, so okay. So we can kind of see what we're doing here. The R seems to mean literal characters. Or replace. Maybe R means replace.
A couple of people in the chat said that the R is it tells it that it's a raw string.
A raw string. Okay, well, so that's what I meant by literal. So yeah, same as literal. So that's good. So that means look for this literal string. This means we're dealing with the regex language when you don't use an R. Okay, great. So R for raw. Thank you for that. Multiple spaces. So we want to find multiple spaces, but this is just.
So it finds the first space and then it says the second space is optional, so it's kind of two or more. So the star means so it's the
Yes,
first
excellent.
space,
Thank
and
you.
then yeah.
Thank you. That's right. So find a series of spaces, a series of consecutive spaces, right? One or more consecutive space, or zero or more. Sorry, one or more consecutive spaces, because you have that. You have the first space, but the second space it says zero or more. I think it might be better to say just a space with a plus after it. One space with a plus after it means one or more spaces, the same thing. So I think I would replace this thing.
But it says it's a literal, like it's a raw string, and they want to replace raw multiple spaces depending on what the input is. Like maybe if you put.
Okay. So R means replace. Then you're saying.
No, I'm saying like the point of this is to replace multiple spaces. So they want to search maybe for multiple spaces. That's why they put the extra spaces there.
Wouldn't the double space mean it? Sorry to speak over. Wouldn't the double space searching multiple times mean it's always looking for two sets of spaces?
Well, yeah, but as I think someone pointed out, the second space is qualified by this star, which means zero or more instances. So that would mean search for one space followed by zero or more spaces.
Yes.
Yeah, and so what I'm saying, but now I'm confused, because if R means raw string, then how come they're using the regex a regex meta character inside of that? That's a little confusing to me. And so, but if they're going to say that is replace multiple spaces with one, then why can't they just
Joseph, raw means just do not use backspace as an escape character. So
do not use backspace as an escape.
So backspace double quote would mean backspace double quote. That's at least what I understood from raw. Doesn't mean just use string. It means do not use backspace. Literally, if it is a backspace n, then the backspace.
Oh, okay. So it excludes. So when you have something that's preceded by R, it means that whatever is in there is to be taken as raw characters, but including meta characters, right?
That's right.
Okay. So anyway, what I was thinking was, why shouldn't this be one space followed by a plus? Wouldn't that accomplish the same thing? Because a plus says match one or more instances of a space. So I think that these two are equivalent, but we'll see. Then she has a function to define simple tokens, I guess, of a string that you send it. So sent equals repunc, that's this thing, that's this compiled expression. Substitute, dot sub means substitute. So you start with this expression. You substitute this thing for this expression in the string that you were given. So this argument, so this is a compiled regex expression. This is a method on that regex expression which is called substitute. And then this is a string that you want to substitute for this expression, and this is the input string, the sent string. Okay, so that's how I read this, right? Does everybody does everybody think that might be right?
That's how I'm understanding it.
Same
okay,
here.
Sent is a sentence, I think, what she means. And so she wants to. So the first thing she does is she substitutes any punctuation. That's what we agreed that this does. Substitute any punctuation with I'm not sure, a space, a /1. I'm not sure what the /1 is.
So /1 is the whole thing which was found in the first.
Okay, the whatever was returned
that's why we have
by this
parentheses,
search.
yeah.
Yeah, that's right. Very good. Thank you. I mean, you obviously know this. You should be teaching this. so yeah, this is the group. So whenever you tell it to find a group, you can refer to that group by /1. If you're asking for two groups, then /2 would be the second group that it found that you specified. So you can have expressions that have multiple sets of round brackets in them. And each set of round brackets returns an expression. And this flags, this says return the first group that you found that I asked you to find in this compiled expression. And so here it is. We have a group that has any punctuation. And so what this does is it surrounds any punctuation with, it replaces any punctuation with, or it surrounds any punctuation with blank characters. So it makes them into so any punctuation mark gets made into a token, gets made into its own token. Let's see, then the next thing is, look at this apostrophe. So now this thing says, find an expression like didn't or don't or whatever, that kind of an expression. And if you find that, that's the compiled expression that we have. Substitute for it. In other words, surround it by the blank spaces. So that's that. And then anything that ends with an apostrophe S, separate off that apostrophe S and make it into its own token. So that's what this is doing. It's saying in don't, it's going to take the word don't and make it into two tokens, do and N apostrophe T. It's going to split off the ending N apostrophe T and make that into its own token. This thing splits off the apostrophe S and makes that into its own token. And how does it do that? It surrounds it by spaces, because that's how we're going to end up interpreting a token. Is we're going to, once we pre-process this list of text into its token groups, then we're going to go pick off all the token groups. And then what does this do? This
takes all the multiple spaces into like
and collapses them into one, right? Oh, wait, this one does, yeah. So this one yeah, exactly what you said. It takes all groups of multiple spaces and just collapses them into one. That's what this does. And then it lower cases the whole string and splits it into tokens. So that's what this little function does.
Joseph, one other comment, don't know whether it's particularly relevant, but just to emphasize, these things are so subtle and tricky. With respect to the star and the plus that you had up above, the difference that I think is in the star case, it'll capture also single empty spaces. And in your plus case, it will only capture double or more empty spaces.
Well, actually, see this one. What I did was this has two spaces, and the first space it's something that has to be there,
correct.
And then the second part is something that optionally can be there. So
right. So
one or more spaces, right?
Correct.
One or more spaces.
Right. So it'll capture the case when it's a star following, when there is no space after the first empty space.
Correct. So it's going to capture the case where there's a single empty space.
Correct.
And this one does the same thing, right? Because I only put one space here. So
but it has to have at least one.
Yes.
Following.
Yes.
So it will only capture starting two.
Oh, I think I see what you mean. Because the second space, the star says 0 or more, so the second space might be a 0. I think that's what he's saying.
Correct. That's exactly what I mean.
Yeah.
In case of plus, your second space is required.
Oh, that's correct. Oh, wait, no, because whatever precedes this plus is the thing you're looking for.
Well,
right?
Maybe.
Yes, and it says 1 or more.
Yeah, so this means one or more space.
Yeah, it'll still capture one.
So these two are equivalent. I claim these two are equivalent.
Only one way to find out.
Yeah, but because see, the thing about these special meta characters is some of them are qualifiers. They need something before them. They need something that occurs before them. The star, the plus,
you're right.
the question mark, and other ones need something to occur after them. Like I gave you.
You may be. Yeah, you may be right.
So
this
plus
qualifies the space in front of it. Okay.
Yes. So yeah, there's a little bit of subtlety here. So, but But anyway, so we're on our way to building a tokenizer. This little function seems to do everything that, well, it seems to do what we need a tokenizer to do. You give it a sentence, it lowercases the sentence because we're not concerned with capitals. You know, that's what this lower does. It lowercases everything. That's what, so sentence dot lower means lowercase that, convert the whole sentence into lowercase. Wherever there's a capital letter, switch it for its lowercase version. And then it splits. But what we've done before we get to this point is we've already separated out all the things that we want to be tokens by putting white space around them. That's what these little things. That's what these things are doing. So yeah. So what about multiple spaces? Yeah. So this is our sort of our tokenizer. So give it a text string. Let's see what it does. Now we're going to join to that. So now we're going to join to an empty string, the result of our simple tokenizer applied to the text. And so then we see what it gives us. And it does exactly what we wanted it to do. It separates out the NT. It separates out the apostrophe S from a word, splits that off. It splits each punctuation mark into its own token. Because remember, this was originally occurring in a row, 2 dashes in a row, but it picked the dashes out and surrounded them by white space. That's exactly what we wanted. Apostrophe, it picked out the apostrophe and surrounded it by white space. It picked out the period, and notice also that it decapitalized all the capital letters and made them into lowercase. And then the question mark, it separated out this apostrophe, it separated out the question mark, and it separated out the quote mark. So this is what we expect our tokenizer to do, and it seems to be doing it, right? Another example, let's see. Now it's going to send this text. It's going to send it the same text, which is this, and just do this part. Surround every punctuation group by spaces. So it does.
It does that.
It does that, but it doesn't. Yeah, but it didn't do the. But our tokenizer did the. Remember, it did the lowercasing, and it doesn't do the lowercasing. Okay. And let's see. It didn't do the. Oh, it did the apostrophe, but it didn't catch this thing. Right? It didn't catch this function alone doesn't catch the apostrophe. So now we have to. So now we show that if we put text 2 through our apostrophe catcher, then it can. Whoops! I forgot to run that. I think, and then I do that, and now it. Let's see. It didn't seem to catch the first apostrophe.
But those are double quotes. Maybe they're not like defined in that.
Oh, okay. So the double quote should also be caught somewhere, because
yeah, it should be caught.
Here it is. It should be caught here. Punctuation. So weird. Okay. Anyway,
the double quotes in front is not part of the string. It's just the way it's displayed.
Oh, okay. Thank you. Thank you for that. Yeah. So the double quote is not part of the string that we entered. Let's go back and check that. Yeah. The double quote merely tells you that it's a string. So this is the actual string we're looking at. So there we go. So this is illustrating the whole action of the whole tokenizer and showing you that it does exactly what you want it to do. And this is just showing you what the parts of it do. So that's fine. So now we can give it a whole bunch of sentences and let's see, list. So make a list. Make tokens, which is a list that maps simple tokens using that maps sentences by applying the function simple tokens. That's what map does. It applies the function. So map takes 2 arguments. It takes a function and then or an operation, and then the second is the string, is an input. And map applies that function, this function, to this input. So that's exactly what we want it to do. And then we can look at our result. And we see that we got a list of, and each, let's see, I want to make sure,
Each sentence.
is that the tokenizer is returning a text string. This thing is returning a list. Okay, so simple tokes is a function. Sentences is a list of sentences.
Mm-hmm.
And so simple tokes is applied, this function is applied to each element in this list of sentences. And so you get a list of lists. So here's this sentence. We can just check that it's doing the right thing. All this happened more or less. It separates out the period. It decapitalizes A. It separates out all the words. So it's doing what we want it to do. The war parts, anyway, are pretty much true. The war parts, anyway, are pretty much true, period. It separated out all the tokens. So it's doing what it's supposed to do. Then, okay, so now remember the other thing that the next thing that a tokenizer has to do is it has to convert your words, all of your tokens, to integers. And then we have to have a way of converting between the words and the integer IDs, the indexes. So she uses this collections thing again. We've seen it before. We have a padding of zeros, an SOS. I'm not sure what SOS stands for. Anyway, it's a 1. We have a function that takes we have a function that's called tokens to IDs. It takes a string of sentences, which would a string of a list of sentences as an input. Let's see, vocabulary count is collections.counter. We've seen that, and then it goes through each element in this sentences. For sent in sentences, for T in sent. So T is a token in the sentence. So it's returning the list of tokens for all the sentences. Sent. Okay, well, this is just a function, and whatever it's given as input, it breaks it up and returns it into tokens. Let's see, vocab is, now it sorts them all. It sorts the result of vote count, key, get, reverse equals 2. It sorts them in reverse. Not sure why it's doing that. It inserts pad. Okay, whenever it sees a 0, it inserts this. And whenever it sees SOS, it inserts this. Let's see, W2ID. This is a dictionary. W2ID is converting words to ID. So it's going through and enumerating the elements in vocab and index. Okay, so it's basically sorting the vocabulary words in reverse order. Then you can enumerate the. Remember what enumerate does is it goes through a list and gives you the 0th element and then that word, the first element and then that word. And so IW is enumerating this list out. And what we're interested in is these indexes. So because the index is the numerical mapping that we're going to make between the token and the numbers. So all it's doing is it's taking this I and W that come out from enumerating and then making a dictionary that has the key as the word and the index as the value. So this is how you can map the token to its value. And then remember, we have to do the reverse. We have to have a way of mapping an index to a word. And so here we have word to ID of token gives you the index for T in sent. So this is going through each sentence in your list of sentences and mapping them to their numerical IDs. So it does this. So it's producing our mapping of the tokens into a numerical space, and then it returns it returns that numerical mapping. It returns the vocabulary, and it returns these functions, word to index and vocabulary count.
My guess about the reverse part is that since it's sorting by word counts, it wants to sort the most frequent words first. So that's why it's reversed. So it's kind of from the largest to the smallest.
Yes, thank you for that. Because I forgot to mention that it's looking at counts. So it's sort of, yeah, the key is the count. And yeah, so it makes sense to sort on the reverse because we want the most important words first. And that's what we ended up seeing in, when we did this before. We ended up seeing that the list in the vocabulary starts with the most frequently used characters. And thank you for that. That's the reasoning behind that. So now here's how you apply this this function. You just get the all the outputs out of it equals tokes to IDs of tokens. And so let me make sure we've done this. Let's do that. And there's our IDs. So it's converted this list of sentences. Each list item corresponds to a sentence, and now it's mapped all of the tokens into their equivalent numerical IDs. So this is what we say when we have an embedding. We're kind of embedding these words into well, the embedding comes later. It's when we convert this sentence into a vector that has a dimension equal to the total number of vocabulary words. Let's see, indexes. Yeah, so these are the indexes of the words that got used. And then we've collected all of our words together in this list. All the words that occurred in any of these sentences are collected into our vocabulary list. And you can imagine that the more movie reviews you start with, the greater your vocabulary will get. And it's kind of like it'll be an increasing curve. In other words, the number of unique words versus the number of reviews that you've collected, but eventually it'll level off, right? I mean, if you collect many reviews, you're not going to find any more new words in your dictionary. So it kind of levels off. And we saw that in our example of the subsample of the IMDb sample, we had something like, what was it, 6,016 or something, 6,016 unique words. So in this is a much smaller set of unique words. It actually can be displayed on almost one screen. So when we examine all of these things, these are what the tokens look like. So we have a padding token, we have an SOS token. I'm not sure what that is, start or end or something. We have
start of sentence.
Start of sentence. Very good. Thank you. That makes sense. Then we have a period. We have a comma. We have I. These all make sense as the most commonly used things. I would have thought that just A would occur more often, but maybe not in this set of reviews. We can see pretty much that these are all, oh, there's A. It's just not as common as some of the other words. And we see the individual kind of tokens that we encounter in sentences. And there they are. So that's the vocabulary. Question, what can be another name of the vocabulary variable above? I'm not sure. I don't know. What else? W2, here's our function that maps, our dictionary that maps a token to an ID. And you can see that it's doing its job. It's mapping the first token to 0, the second token to 1, the third token to 2, and so on. Refresh your memory. There's the first, second, and third. The last token is names, and it got mapped to the largest number, 51. So we have 51 words in our dictionary here. So that's pretty much the regex and how it gets used. then she reminds us that string has its own uses that are, it has methods called find, substitute, start, end. So you can do stuff. You can put qualifier. You can put you can add a method to a string. String.find gives you a way to find. So you give it a string and you tell it you want it to find that string. So for example, so you could write text equals blah blah blah. And then you could say ah.find and see what it does. Let's call this something, and then see what we got. Oops, I don't like that. Find takes at least one argument and none given. Oh, sorry, I meant to give it the argument. I need to give it the text, sorry. I'll just go back to what I had. I need text. I need to write this with the right syntax. Text.find of what I want to find goes in here. So, and it tells us that, I guess that it returns the number of times it found that, or maybe the index of the last, let's see. So there's 3 instances of AH, and it says 2. I think that 2 refers to the index of the 3rd instance. I'm not sure.
The first one.
Oh, the first. Oh, the index. That's right. The index of the first instance of AH. So
it's 0 base, so 0, 1, 2. Yeah.
Exactly. Thank you.
Find all. I think finds all the instances. Like find underscore all.
Let's see.
I think it's find underscore all.
Thank you. So we do that, and then didn't
like
maybe
that. Maybe something else, yeah.
String object has no. Well, we can look again. What we have to work with here. We have substitute method. We have a start method. We have. Oh, fine. Oh, maybe what we need to do is do this. That'll tell us everything we can do with strings. So let's see. String objects.
It's find all, no underscore.
Oh, find all, no underscore. So I'm wondering, okay, let's do that. Find all, no underscore, and then see what we got. String object has no attribute, find all. Huh, well, let's try something else. We can figure out what properties of what we have to work with by asking what the properties of this string are, and see what we can do to it. We can ask for, these are all the methods that we can apply to it. We can split, we can strip, we can find. It has a method find. Well,
it has the right find if you want to look from the right, like rfind.
Rfind, that's great. And then lfind. Oh, okay, let's try that. Let's try rfind and lfind. And we think we know what that'll do. We think that rfind is going to find this one, is going to tell us the index where this starts. So let's figure out what we expect. It's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It should. We think we're going to get 10 back when we do rfind, right? Rfind. And then let's see what we got. Yeah, so we got 10. And then we can do lfind, and then we think we should get back the same 2, right? It doesn't have a middle find, so oops, lfind, text.lfind.
That's just find.
Oh, that's right. That's right. Find already, it doesn't have a method lfind because find finds the left-hand side. Okay, great. Thank you for that. So we got the 2 back. Anyway, there's other things we can do. We saw that we use the method strip. I think we use a split method. Split splits on spaces. So, or it splits on whatever you want. So you could do something like blah let's say you had a comma-separated list of things. So let's say this would be a more interesting application. Suppose you had a comma-separated list of numbers, 12, 14, 22, 17, 31, and then you give it that list, and then you can say text.split. And you have to tell it what you want to split on. So you could split you want to split on commas. So let's see what happens if we tell it to split on commas. And it did what we expected it to. This is how you process a comma-separated list, which you sometimes have to deal with. You could split on spaces, for example. If I did it that way, if I split on spaces, I would get a different result. It included, see, I told it to split on spaces, so that means I force it to include the commas in there. Anyway, so this is just ways of dealing with text. So you know, Python has ways of dealing with text, has its own string methods, but regex is much more powerful. String methods are easier to understand. They express the intent more clearly. Regex has a much broader use case. It's much more powerful. Regex is used not only in Python, but in other languages. And this is something I didn't know, that regex can be faster at scale. In other words, if you have lots and lots of text to process, regex is very quick. I guess because it's compiled. You actually compile your regex expression, as you saw above. So that's our, oh, and this is interesting. You can, so let's try to understand, let's break down this example. So there's Unicode characters that I'm going to figure out what, because I can figure out what these are by putting them in a, insert cell below. I'm going to put these characters in there, but now I'm going to say that it's a markup, and then I'll be able to see what markdown. Let's see, I can do this. They just map directly, and I thought I was going to see the code for it. Anyway, there are actual Unicode sequences that give you these funny characters, and I don't know what they are. What we've done here is we've created a message composed of these special Unicode symbols, and this is kind of interesting. He makes a function called regex frown, which is regex compile this sequence that is either the yellow frown or the green frown. That's what this means. And then she makes this thing regex frown.sub. So you take the frown and then you substitute for it a smile, and then you apply it to the message. Remember, the message was this sequence of characters. So this is compiling a regex function that looks for either a yellow frown or a green frown, and then this function says look for the yellow or green frown and then substitute it for a smile character in this given message. You have to give it an input message. So then you do that, and it comes up, the two frowns are replaced by yellow smiles, which is what you told it to do. Okay, and then Rachel goes through this advice for when you use regex. There are two kinds of errors you can make. One is where you match a string that you didn't intend to match, and another error is when you miss matching a string that you wanted, that you were supposed to match. So you have to check your regex expressions. You have to test them. When you come up with a regex expression that you think is going to do the job, you should test it on all kinds of instances, all kinds of test cases, to make sure that you don't get any of these type 1 or type 2 errors. Okay, so a lot of times you'll come up with, you'll brainstorm a regex expression, and you'll say, oh, this I think is going to work. And then you have to try it out and prove to yourself that it really does work by looking at different cases. Make sure that it doesn't match things that you don't want matched, and that it doesn't miss things that you wanted to catch. All right, so, and these are some resources that she pointed to, a cheat sheet. Let's see what that has in it. This, yeah, this is kind of convenient. It goes over much of the things that we did. There's more to regex than what we gave, but what we gave in this lesson is like 90% of what you'll ever need. So there's always, when you learn a new language or something, the best thing to do is to learn the most important 90% of it, the stuff that's going to handle 90% of the cases, and then you can learn the rest of it. And that's what we did today. We learned, we learned the stuff from regex that we'll need, that will be useful 90% of the time. And then sometimes you'll have to learn more. You'll have to go to something like this, a more comprehensive spreadsheet, to find more subtle features of the language. Because it has a lot more things you can do with it. You can look for hexadecimal digits or octal digits, blah, blah, blah. There's a lot of fancy stuff you can do with it. You can even do I guess you can make if then else statements too, which we haven't gone into. But anyway, this is a kind of introduction to regex that I wish I had seen many, many years ago. So I wouldn't have just avoided it all this time thinking that it was just a bunch of gibberish that I didn't want to learn about.
I'll speak for myself. I'm glad we did this together.
Yeah.
Because doing this alone would be, and even reviewing it would be hard.
Well, especially since we had Gidris to help us, because he seems to really know this very, very well. So that was great. And thank you for that. All right, well, I actually got done. I didn't think I was going to be able to finish all this stuff, but I did. Does anybody want to talk about anything? Raise any issues or questions that they want to talk about?
It's pretty straightforward.
Great. Yeah, so now
we have class next week.
Yeah. Yes, we do. Is there some special day that is next week? Some special day that I should know about? Or it's February 8th, right? February 8th. Nothing special. We'll have a class. What was I going to say? Okay, this brings us to the end of. I think it brings us to the end of the classical approach to natural language processing, and I think from now on we're going to do. Maybe there's one more lesson, but pretty soon we're going to start using deep learning for natural language, seeing how deep learning is used for natural language processing, and then it's going to get really interesting.
Awesome.
So, yeah. So if there are no issues that people want to talk about or things that people want to raise, then I'll see you guys, and you people next week.
Thank you.
Fantastic.
Thank you all
so much.
Thank you.
Thank you all. Bye.